these two positions, and 12 people have applied for the one position, the engineering position, and 17 applied for the managerial position. How many different ways can a position be filled? We assume that the 12 people are different than the 17 people. 204. Where'd you get 204, Rhoda? 17 times 12, right? In other words, if I drew the tree diagram, this is really a waste of time, so I'm not going to do it, but I got 17 possibilities on the first choice, right? And then regardless of who I pick for the one position, then I have 12 options for the next position, right? 12 options, and so 17 times 12, it should be 204. Okay, great, so let's put, what's this, problem 2 is A, 204, and that's a result of either 12 times 17 or 17 times 12. How about, let's look at B, okay? A restaurant offers several choices for a 3-course dinner, right? I get an appetizer, I get an entree, and I get a dessert, okay? And for $12, I get my options, okay? So if they have 5 appetizers, 10 entrees, and 4 desserts, how many different meals can I kind of compose? Chelsea?
200.
And how'd you get that?
5 times 10 is 4.
Yeah, because I've got these 3 choices, right? 3 stages of the dinner. I'm making a choice at each one, okay? And this rule of counting says, yeah, it's 5 times 4 times 5 times 10 times 4 equals 200 dinner choices I can put together, combinations. Let's look at the last one. An access code consists of a letter followed by 4 digits. Any letter can be used. The first digit can't be a 0. And the last digit has to be even. How many different ways can I compose the access? Garrett?
93,600.
93,600, okay? That's correct. Okay, Garrett, okay, so we're going to put the answer over here, because that's the right answer. 93,600. How did you get that answer?
It would be 26 letters.
All right, so the first, let's look at the first one. The first one is a letter, right? And how many ways?
26.
There's 26, right? So the next choice that I make or randomly choose to assign is what? A digit?
Except 0.
But it can't be 0, can it? So how many different ways can I choose this digit? 9. Not 0. Here's a digit. Here's another digit. Are there any constraints on the second and third digits? So how many different ways do I have the option, or can I assign a number to that second and third then? Cassidy? Well, let's look over here. Let's put a little 1, 2, 3, 4, 5, 6, 7, 8, 9. Got to be one of them, right? How many of them are there?
10.
There's 10, right? So now the last one, it's got to be another digit, but it's got to be what? Even. So how many choices have I got over here?
4.
That's it, right? So those are the 10 digits times 4 equals 93,600. Okay, good job. All right, let's look at number 2 there. It says, what's the probability of randomly selecting the correct access code on the first try? So we just randomly try to guess this access code. What are our chances?
1 in 9,000.
Yeah, pretty bad, aren't they? I mean, look at it. There's one way we can get it right, right? 1 over 93,600. That's the probability of getting it right first guess. Everybody see that? That's why a lot of people don't win the lotto, right? I mean, that's why it's hard. What's the probability of getting it wrong or incorrect? Probability wrong on first guess. How many different ways can we get it wrong? 9,000, 90,000, 93,000, right, yeah, somebody else say it other than me, okay?
93,599.
Yeah, 93,599. 93,599 over 93,600. That's why the state makes a lot of money on the lotto tickets.
That'd be the pessimistic approach.
What's that?
Pessimistic approach.
Pessimistic approach, yeah. Okay, this is the optimists. All the optimists are over there, right? I don't even think, Chris, that's a pessimist. That's the realists over there, okay? The pessimists are, you know, like they don't even play. Okay. Any questions? Let's take a look at where these probabilities come from. We introduced the idea of probability a little bit here, okay? And here's